Hello students, here we come to the second part of nuclear magnetic resonance spectroscopy. So first we are going to study how an NMR spectrum is read. NMR spectrum is actually a plot of intensity of NMR signals versus the magnetic field. It means like on x-axis we will be having the magnetic strength of the magnetic field, and the y-axis will give you the absorption intensity. Now in NMR spectroscopy, we are actually studying the proton, and the question comes that like when we are dealing with the structural determination, actually NMR spectroscopy is useful in structure determination or and interactions basically. So, and we are actually determining the proton. So why should the proton nuclei in different compounds behave differently so that we can get the structural determination of the compound? So the answer to this question, it lies like that with the electron that is surrounding the proton in covalent compounds and ions. Now since the electrons are also the charged particles like the protons, so they also have the magnetic field around themselves. Now this magnetic field actually um, shields the proton from the external magnetic field. So, since the electrons are charged particles, they move in response to the external magnetic field and so as to generate a secondary field which opposes the stronger field applied. This secondary field shields the nucleus from the applied field. So, the intensity of magnetic field has to be increased in order to achieve the resonance. What we are actually doing is we are resonating our nucleus from the lower energy state to the higher energy state. And for that resonance, it requires certain amount of energy. But my surrounding electron, it is shielding that incoming magnetic field. So we need to increase the amount of magnetic field so that say the amount of energy required for flipping of the nucleus can be made available. Now there has to be certain reference. So in case of an NMR spectroscopy, generally tetramethylsilane is which is also referred to as TMS, is used as a reference compound of choice for proton and carbon nuclear magnetic resonance spectroscopy. Why TMS is taken as a reference compound is because it is chemically unreactive and is easily removed from the sample after the measurement. Moreover, as you can see that here there are 12 hydrogen atoms which are all in the same environment. Okay, so we have the same chemical environment of all these 12 H atoms, which gives a very single sharp NMR signal that does not interfere with the resonance normally observed for the organic compounds. Moreover, the silicon is very slightly electronegative. Now, when it is very slightly electronegative, it is not delocalizing any electron surrounding the proton nuclei, the H atoms. So, protons are highly shielded. We are going to discuss this shielding and deshielding concept in detail in later slides. But how from here, the protons are highly shielded, and so the NMR peak is a field of most of the NMR peaks. Now, can you can be able to see this is how since the protons all have the same magnetic moment, we might expect all the hydrogen atoms to give the resonance signal at the same field, but fortunately for chemistry application this is not true. This is you can see the NMR signals of different in case of different compounds. So we have this positioning of NMR signal, it all depends upon the number of H atoms, and it depends upon the actually the surrounding of the proton. Now this shift of the signal is referred to as chemical shift, and it is defined in terms of the frequency of resonance expressed with reference to a standard compound, which is defined at 0 parts per million. So this is how you can this was all I was talking about, the upfield and the downfield shift. The upfield shift is because of the shielding effect. When the nucleus is shielded, I need to increase the magnetic strength of the magnetic field in order to flip my nuclei. And in case of deshielding, when the electron is being withdrawn from the surrounding of the nucleus, it becomes deshielded. And when it becomes deshielded, I need to give a little less amount of energy so that my nucleuses can flip. So if the electron density about a proton nucleus is relatively high, this induced field due to electron motion will be no doubt it will be stronger, and if the electron density is relatively low. So the shielding effect in such high electron density cases will therefore be larger, and you need to give higher external field will be needed for RF energy to excite the nuclear spin. Such nuclei are said to be shielded. However, elements that are more electronegative than carbon should exert an opposite effect, means they are reducing the electron density. And such proton nucleus, they are deshielded. And when they are deshielded, I need to give lower external field will be needed for the RF energy to excite the nuclei, and such nuclei are deshielded. Now, coming to the signal strength. Signal strength means the magnitude or intensity of NMR signal. Now, that is displayed along the vertical axis and is proportional to the molar concentration of the sample. Now, for example, if we take NMR spectrum of equimolar amounts of benzene and cyclohexane in carbon tetrachloride solution, the resonance signal from cyclohexane will be twice as intense as that from the benzene, because the number of hydrogens are more in case of cyclohexene. It has twice as many hydrogens per molecule. So this is an important relationship when samples incorporating two or more different sets of hydrogen atoms are examined, since it allows the ratio of hydrogen atoms in each distant sets to be determined. So the intensity of the signal, it all depends upon the number of hydrogen atoms. Like we studied in case of TMS, we have a very sharp peak since it was having 12 hydrogen atoms. So the intensity depends upon the number of proton nuclei that we have in the compound. This is the NMR spectrum of ethanol. We have the first peak, that is of CH3. These H3H are in the same chemical environment. So we have you can see the peak here. We have, this is for CH3, then we have the next peak that is for CH2, and then finally we have the third peak that is of this H from OH. And this one is more deshielded. Why? Because O is the more electronegative than carbon, it is more withdrawing, and so uh, it is the deshielded one, and these are the shielded ones. CH3 and CH2 are the shielded one, and the intensity and the height of the peak determines the number of H atoms we have in the compound. So this is the final figure which shows the number of H atoms we have, and this is the NMR spectrum of ethanol. So CH3 TMS, this figure shows the positioning of TMS, the shielded and the deshielded proton nuclei. So the what informations do we get from the proton on NMR spectrum? That is the different non-equivalent hydrogen atoms we have in the molecule, the number of different peaks we have, the number of different non-equivalent hydrogen atoms we will be having, the ratio of the number of equivalent hydrogen atoms, this is shown by the areas under the peaks, the chemical environment of the equivalent hydrogen atoms, that means the position of the peaks. So NMR spectroscopy, this is an important analytical technique which is actually used for studying for determining the macromolecular structure. It allows the visualization of single atoms and molecules in various media and solution as well as in solid state. It is a non-destructive technique and gives molar response that allows structure, elucidation, and quantification simultaneously.